This is our last lecture in the series of engineered materials. We started off talking about ordinary materials. At a slightly larger scale, we talked about mixtures. At a slightly larger scale than that, we talked about metamaterials. And now at the largest possible scale for engineered materials, we're talking about photonic crystals. Roughly, this is on the order of a half of a wavelength. The spacing is large enough that a wave traveling through a photonic crystal bounces and scatters off of all the different interfaces, and we get this overall very complex interference, which leads to the properties of photonic crystals. Roughly, I will divide photonic crystals into the band gap type of materials and then the dispersive type of materials, or photonic crystals. Very often we call photonic crystals band gap materials. I don't like that title simply because there's very useful photonic crystals that don't have band gaps. So it doesn't make sense to me to call something a band gap material when it may not have a band gap. So I use photonic crystals. Maybe electromagnetic crystals will be a little bit better title, and in fact I've seen that. But I guess the consensus is we call these photonic crystals. In the early 90s, what we've known for a long time, Schrodinger's equation describes the flow of electrons through a periodic potential. So imagine an electron flowing through a semiconductor, and we learned all kinds of things from that. We learned how to control electrons in semiconductors and make computer chips and a bunch of stuff. So that's very cool. In the early 90s, we connected the dots between Schrodinger's equation and the wave equation. And if we analyze the wave equation, the electromagnetic wave equation, in the same way, suddenly we get bands. Now, in fact, I can pull some old papers from the 50s and 60s that also show electromagnetic bands. For whatever reason, it didn't become popular at the time, but in the late 90s, those dots were connected again, and suddenly we realized, hey, we can control electromagnetic waves inside these periodic structures the same way we can control electrons in silicon and semiconductors. So where we had electron bands, now we have electromagnetic bands or photon bands. So in an analogy with this band diagram, we will call this a photonic band diagram. And lots of cool things come from this. The first subject area is the band gap engineering. This is where the photonic crystals act like an insulator, and in fact they reflect. They act like a mirror throughout. We want to understand a bit more about the origin of band gaps, and it starts with the Bloch Theorem. And we've talked about this a bunch, but essentially the electric field is decomposed into two components, this amplitude term and this plane wave phase term. And it's actually the amplitude term that takes on the same periodicity as the lattice that the wave is propagating through. So in fact, this is how we would express the amplitude term. So that's the Bloch Theorem. Next, we start with Maxwell's curl equations. We substitute one into the other, and in this case, we are taking the second equation, solving for the electric field, and then substituting that expression in to eliminate the electric field and have one equation just in terms of the magnetic field. So that is the wave equation in terms of the magnetic field. We can write the Bloch theorem in terms of the magnetic field. Now we substitute this expression in for the magnetic field and turn our mathematical crank, and we end up here. The last equation, it turns out, is what's called an eigenvalue problem. And we can just, in general, write our eigenvalue problem in this form. We have some linear operation. In this case, it's the cross products operating on the magnetic field. And on the right-hand term, we have some scalar constant times that magnetic field. We can think of an eigenvalue problem as a test. We'd make a guess at the magnetic field. If we do this complex mathematical operation on it and really end up with the same thing again, just potentially scaled by a constant, then that guess to the magnetic fields is a solution to the eigenvalue problem. It turns out eigenvalue problems have an infinite number of solutions. Numerically, we found out last semester, we somehow have to truncate this, and we really can only calculate a finite set. But in principle, eigenvalue problems have an infinite number of solutions. And we can calculate those as we take our grid resolution out to infinity. So we have these eigen solutions. And it turns out the field can take on more configurations than what's described by the eigenmodes by themselves. And it turns out any linear combination of those eigenmodes is an allowed state. So we would write that as h sub beta, that's our eigenmode, and we have some constant multiplying that. So it turns out the magnetic field is any linear combination of those eigenmodes. Now, we can solve this a number of different ways. If we solve this using a variational calculus, we get a very interesting theorem from that, which says that the lowest energy state, so the first eigenmode we calculate, has to satisfy this equation, has to minimize this equation. So let's look at how to minimize this. Well, we can minimize this ratio by maximizing the denominator. Well, how do we do that? Notice we have the permittivity multiplying the electric field squared. Well, the conclusion is that the electric field prefers to be in the dielectric. So for that first zero order mode, the lowest order eigenmode, the power in that mode prefers to be in the highest dielectric constant. So we're going to pull that information again in a little bit to explain why there are band gaps, why there are potentially band gaps in periodic structures. In one slide, this is the origin of the band gap. So for simplicity, let's look at one-dimensional periodicity. So what we're looking at are slabs of alternating refractive index. We have low index, high index, low index, high index, low index, and so on. That goes off to infinity. We know that our modes have to take on the same periodicity as the structure they're in. So let's look at this lower order band. This is our first order mode, and it has the same periodicity as the structure it's in. It doesn't necessarily look like that. It doesn't look like squares, but it has the same periodicity. We also know from discussion on the previous slide that the power in this first order mode prefers to be in the high index regions, or the high dielectric constant regions. So that's where we place the maximums. And then in the minimums, we have the least amount of power. Now this does not mean that there's no power in the low index regions, or that all the power is in the high index regions. It's just the majority is shifted here. Now we move to the second order band. The second order band is forced to be orthogonal to the first order band. So that means the power jumps from the high index to the low index. Very often this first order band, for this reason, is called the dielectric band, because the power prefers to be in the dielectric. And the second order band, called the air band, because the power jumps and prefers to be in the air, or the low index regions. So now let's think about this. We have two waves with the same period. However, the lower order band must have a higher average refractive index because the majority of the power is in the high index regions. This one, the majority of the power is in the low index region. This one has to have a lower average refractive index. So we have two waves that have the same period but different refractive indices. How on earth do we reconcile that? The only way to reconcile that is if they are also different frequencies. So that is why we have a band gap. There has to be a difference in frequency here in order for these to have the same period, yet two different effective refractive indices. And that is the origin of the band gap. Now let's think about what we need to do to get a complete band gap. So what we'll do is we'll plot some two-dimensional lattices. We'll look at both the TE and the TM modes and see what happens. Here we have a lattice of dielectric cylinders, small dielectric cylinders, and we plot the bands for both TE and TM modes. Well, what we see is that we have a band gap for the TE mode, but not for the TM. So the conclusion here is that dielectric globs are preferential for band gaps for the TE mode. Next, we'll look at a dielectric lattice that's connected vanes. And so you can see a small section of that lattice here. Well, now we have a band gap for the TM mode, but not for the TE. There is no TE band gap. So what we conclude is that the TM mode, or H mode if you will, prefers to have connected vanes of dielectric. Well, neither one of these lattices have a complete band gap. So somehow we have to do both. But maybe there's more. We're also very interested in the symmetry. And it turns out the more symmetry the lattice has, the greater chance for band gaps. Now let's think about why that is. A wave picks a direction through a lattice, and it sees a particular Bragg grating. As we change directions, it sees a different Bragg grating. So really, there's a band gap in every direction through a lattice. However, since the Bragg gratings look different in each direction, those band gaps are offset. And we need all of those band gaps to overlap over some frequency region in order to have a complete band gap. So the more symmetry there is, the more similar that Bragg grating looks in all these different directions, and a greater chance we have for a band gap. So on this slide, that's really what we're showing. The lattices that have the greatest symmetry are the ones supporting not only the band gaps, but the widest band gaps. So we have three things now. We want high symmetry for a band gap. We want dielectric blobs to support the E mode band gaps. And we want connected vanes to support H mode band gaps. So if we somehow can pull all of this together and do all three at the same time, we'll have a lattice that supports a complete band gap. So here's a lattice that does that. We have an inverted hexagonal array. What's shown in black here would be some refractive index or dielectric constant and big air holes. So we used a hexagonal array because that has the greatest symmetry of the 2D lattices. We have these thin little vanes, and that's for the TM or the H mode band gaps. And we have dielectric globs. Those support the TE or the E mode band gaps. Well, if we do all this together and give it nice high index contrast, what we see is that we have a complete band gap. So all frequencies, all polarizations in that band are not allowed. They will reflect. They will be cut off. And so that's the rule of thumb for realizing a band gap. High symmetry, dielectric globs, connected with vanes. We can think about the three-dimensional equivalent to that, and we go to a diamond lattice, and we also give it inverted symmetry, which makes more sense from what we had on the last slide. And it turns out of the Bravais lattices, this has the widest band gap. We can achieve a band gap also with the lowest refractive index using this type of lattice. Well, we alluded to this before, but there's something that beats this, and that's an aperiodic lattice. And why does it beat it? It's because here the Brillouin zone, we have to account for the statistics of this, and the Brillouin zone, as it turns out, gets a little bit blurred, and that gives it effectively more symmetry. So the Bragg grating looks more similar in each of the directions due to the randomness, and it turns out we get a wide band gap. So these are the widest known, strongest band gaps. The other thing that amazes me is that the band gap occurs at such a high order band. This is something like the 30th or 40th order of bands up here is where we get the band gap. That's very surprising to me. Let's now talk about some devices based on band gaps. Well, a big one is waveguides. And in integrated optics, we can have a square array or some kind of planar array of holes, and this would have a band gap, and so light at some frequency would be cut off. We can have a defect running through the middle of this lattice, and suddenly we have a waveguide. The waveguide here is not guided by total internal reflection. It's guided more like a metal waveguide. It's just not allowed. It's cut off here due to the stop band. So we can make a waveguide. There's also photonic crystal fibers. Now, some photonic crystal fibers do not operate from a band gap. It's other principles, more total internal reflection. However, if we surround an air core with something that has a band gap, we can guide energy down that. Also, if we have a three-dimensional lattice and we put a defect in the middle of that lattice, we can trap energy here, and we can store it and do some interesting things with that. We can make very highly resonant cavities. I'd say it was 10 years ago, it was all the rage in the optics community to do very tight waveguide bends based on these photonic crystal lattices. And tight 90-degree bends. Also on this lower left here, there's even a tighter bend than 90 degrees. And so this was very attractive in integrated optics, where you want to put light on a chip. And normally, in a normal waveguide, there's a certain bend radius. If you bend it too tight, you lose light. Well, now suddenly there's a way that we can have very sharp bends and get near 100% transmission through some very tight bends. So that has the ability to miniaturize little optical integrated circuits. There's also antennas. This is now at radio and microwave frequencies that can be based on these electromagnetic band gap materials. And here's the claims from the literature, that we can increase radiation efficiency by suppressing surface waves. The electromagnetic band gap materials are a more efficient reflector than metals. Supposedly, we can get higher directivity due to the angle of incidence sensitivity of the band gap. And the claim is that we can get higher directivity out of a band gap material than we could otherwise. There's all-dielectric horn antennas. I have a picture of that in a couple of slides. And there's also additional degrees of freedom now to tailor polarization in your antenna. So here's one example of a highly directive antenna based on electromagnetic band gaps. So what we see is we have a metal backing, we have a half wavelength little Fabry-Perot cavity, and an electromagnetic band gap on the top here. So this serves as a very angle-dependent mirror. It will only act like a Fabry-Perot over a certain range of frequencies. So overall, we get this very directive beam from it, because if it's outside this certain angle, well, we don't have the Fabry-Perot cavity, and it doesn't act like an efficient antenna. Here's a concept that some folks are looking at. This is all dielectric now, or can be all dielectric, and instead of using metals, we use an electromagnetic band gap material. So these lattices would have stop bands, and so we could excite this with radiation within that stop band, and it would radiate, just like a horn antenna. I'm not sure how practical something like this is, but there's folks working on it and can do it. There may be reasons that we can't use metals, and maybe we're forced to do something like this. Okay, on to our second big topic, and now we're going to talk about photonic crystals that don't necessarily have band gaps. We're exploiting other properties in them. So I call this dispersion engineering. Our first subject that I'll touch on just very briefly is phase group and energy velocity. And we have a lecture coming later on slow waves where we're going to talk about this in much more detail. Suffice to say that these are all different. And the phase velocity, we're looking at the wave. If somehow we could see the wave, we would look at the speed that appears to be moving and say that is the phase velocity. And from that, we could extract a phase refractive index. And in fact, that can approach infinity. Then we have the group velocity. And essentially, if we have a pulse composed of a bunch of different frequencies, we know due to dispersion that they could potentially be traveling at different speeds, so that wave packet as a whole slows down. So the group velocity is different than the phase velocity when there is dispersion. If there's no dispersion, group velocity and phase velocity are the same thing. So we have a group velocity, we can talk about a group refractive index. Then finally, there's the energy or the power velocity. And in linear materials, this is the same as the group velocity. We have to go nonlinear to see a difference there. That I've identified, there's at least 3 different flavors of dispersion. The first one's the material dispersion. The pure bulk material itself may have a different dielectric constant depending on frequency. Or maybe we're using a metamaterial and we're operating near a resonance, so the dielectric constant changes a lot. But here the actual bulk material properties are changing as a function of frequency. So that will introduce dispersion. We also have the spatial dispersion. This is where we were talking about index ellipsoids, Brillouin zones. Depending on the direction a wave is traveling, it sees a different average refractive index or different effective dielectric constant, depending on direction. So that's dispersion based on direction. We also have modal dispersion. Like in a waveguide, we can calculate different modes. Each mode has a different effective refractive index. So each mode travels at a different speed. So dispersion is really somehow something is changing with respect to frequency or with wavelength. And we can have the pure materials doing it. We can have things change as a function of the direction of the wave, or different modes travel at different speeds. And we can play with all of these and in combinations. Okay, so we've mentioned this a few times too. The electromagnetic band diagram, or the band diagram, is missing information. It's a very quick way of assessing where the bands are, looking at band gaps and stuff like that. And we would trace the perimeter of the irreducible Brillouin zone. But the reality is we have to calculate every point in the Brillouin zone to see all of the information. So what we do, we set up a double loop and we march through the Brillouin zone. And every point in the Brillouin zone, we calculate all of the eigenvalues. So let's look at this three-dimensional diagram where we have this double loop and we're sweeping through this. At each point, we calculate the eigenvalues and plot them vertically. Then we move to the next point, calculate the eigenvalues and plot them vertically. Move to the next point, plot all the eigenvalues and plot them vertically. When we fill in all of this space and our points are close enough, what we'll see is all those eigenvalues group together and form bands. This is the full, complete band diagram. What we showed on the previous slide was missing information compared to this. But when we're looking at dispersion engineering photonic crystals, we really need this full set of information to do that. So the next step, let's grab one of the bands. Let's grab the green band. So now we're plotting the green band as a continuous sheet. This vertical axis is frequency. So if we construct a plane, for example, at normalized frequency 0.6, here's a plane, and we look at where that intersects our band. This plane is constant frequency, so this intersection we would call the isofrequency contour. And if we plot that, it's the red line down here. That's the isofrequency contour where we're showing it above. Likewise, if we change frequencies, we come up to maybe that's 0.7 normalized frequency. That intersects the band around this region, looks very square. So we see this square isofrequency contour. If we raise the frequency even more, now we intersect along this little tiny region, and we see the iso contour. And at some point, the frequency would be above the band, and there is no isofrequency contour, or below. Again, no isofrequency contour. So these contours are a function of frequency. It would move around as we slide this plane up and down. So it's from these sets of iso contours that really we do the majority of our dispersion engineering. And the other connection we need to make is that these isofrequency contours are the same thing as index ellipsoids. And it's really telling us what is the magnitude of the K vector as a function of direction through the lattice. And that's exactly what the index ellipsoid does as well. We do the same thing. We look at the first order band. What we can see is that the iso contours are mostly circles. And why is that? This lower order band is so low frequency that the wavelength is so large relative to the photonic crystal, it's not even acting as a photonic crystal. It's acting more like a metamaterial or a mixture. And we're really just seeing these circular iso contours. The wave sees the same average in all directions. Nothing interesting happens really until you start to resonate. And so maybe at the edge of the band, and here we like to design devices on the second band, but way down low, it's really not even a photonic crystal. So those isofrequency contours are circles. Or if the unit cell was not square, we'd see ellipses and other things. So here's really the snapshot. When we look at these isocontours, we don't plot the full bands. That's just to illustrate where we get these isocontour from. These are the types of maps that we look at. So this first one on the left is from the first order band. As we mentioned, for the lower frequencies, it's circles until we get out here, and then maybe some interesting things starts happening, because this is where the lattice becomes resonant. Second order band, this is pretty cool. We already know that these flat regions are very interesting because that's where self-collimation happens. So there is a lot of information here. And even sometimes these curves here are very interesting because we can cause negative refraction to happen just due to the dispersion in the lattice. We don't have to have a negative refractive index for that. In fact, we'll explain this in a couple of slides. So really what I've talked you through is the toolbox for doing dispersion engineering. Let's think about some devices and some phenomenon based on engineering the dispersion of the lattices. I'll point out again, we're doing some neat things and there's no band gaps. So again, I don't like calling these electromagnetic band gap materials because we're getting some cool things to happen and there's no band gaps. So on to negative refraction. So here's how we can predict negative refraction, and this is not due to negative refractive index. There's some papers in the literature that show that their lattice refracts negatively, and they call it negative refractive index. And in fact, they've gotten confused. They don't have a negative refractive index. They just have strangely shaped isocontours. So let's think about how this happens and look at phase matching. Let's say we have air, and so it has an isocontour that's a circle, because no matter what direction a wave tries to go in air, it sees the same refractive index. So we have an incoming wave vector, which connects the origin to the point on a surface. And we also know that we have power aligned with phase. We want the transverse component of our wave vector, so we drop a projection down. This orange line is the transverse component. For convenience, we copy it over here. We drop a projection down until we hit the isocontour again, and then we see here's our phase. It bends a little bit, but the power is defined to be normal to that isosurface. It's traveling to the lower left now. That's called negative refraction, and phase and power are going in different directions. What does that look like? Well, here's an example. We have wave fronts here in the incident region, and the beam is traveling in this direction. That's the power. When we refract negatively, notice the orientation of the phase. The wave appears to be going to the lower right. However, the power, the actual beam, is traveling to the left, and that's called negative refraction. And once it exits, it looks like in the applied region again. So we can have negative refraction without negative refractive index, just due to the dispersion of the lattice. Another area that dispersion engineering crops up a lot is chirped fiber Bragg gratings. If we send a very short pulse down a very long optical fiber, there's a number of mechanisms that occur that can cause this, but the net result is each color down that fiber, and if we have a short pulse, there's a pretty broad range of colors, each color travels at a different speed. And by the end of a very long haul of fiber, our short pulse has been dispersed. So that's what we're drawing right here, a nice dispersed pulse because of dispersion in the fiber. Well, let's look at a Bragg grating. So we simulate reflectance from a Bragg grating. Here's the reflectance. If we look at the phase response, here's what we get. Notice in the stop band this essentially linear phase. Well, we can design Bragg gratings to introduce dispersion in the reflection mode that's opposite to what the fiber did. So we can disperse, we can stretch our pulse, because here it looks like the red light traveled slower than the green and blue light. So if we go into a Bragg grating and now reflect the red light first and the blue light last, we can recompress our pulse. We introduce dispersion that's exactly opposite to what the fiber did, and we recompress our pulses. And so that's called dispersion compensation. But again, we're engineering the dispersion in a periodic structure. Slow wave devices. I'll be brief on this because we have an entire lecture coming up on slow waves. Suffice to say that dispersion causes slow waves. And in fact, we have to introduce dispersion in order to slow a wave down. And more on this in the lecture coming. We have graded photonic crystals, and these really come in two different flavors. The one really isn't even a photonic crystal, but imagine we have a distribution of holes, a lattice of holes, and the spacing is so sub-wavelength that it's really not a photonic crystal. There's no wave scattering. We chirp the size of the holes. We can essentially grade refractive index, and in fact, we can bend beams through lattices like that. Alternatively, we can operate in the photonic crystal region where we're chirping the size of holes, and we know as we get near the band edge, or the edge of a band, that it becomes very dispersive. We might even know this from circuit theory and when we design filters. When we get near the edge of the filter, the phase goes crazy. Well, here what's happening is we're chirping the size of the holes, and we're sort of surfing that band edge to tune refractive index by adjusting the hole size. And in fact, we can turn beams by doing that. In the end, we're doing the same thing. We're grading refractive index. However, we're using a photonic crystal effect in one case where you're riding the dispersion curve near a band edge. In the other, the holes are spaced so sub-wavelength that it's really just an average effect producing the graded index. And another thing that was quite popular some time ago was hyperdispersion or super prisms. We can illuminate these lattices that have a very strangely, anomalously shaped dispersion curve, and in fact, we can spread out the colors extraordinarily powerfully. We can send red one way and blue another, and the span in angles is beyond anything that we could realize with nature. So that's interesting for spectroscopy and other things for sensing. So that was a brief survey of what folks are doing with photonic crystals. I added this last section, which is another type of dispersion engineered self-collimation. We're doing a lot of research in self-collimation here, and really up till recently, it's been, I'll call it a useless phenomenon, really because it only takes waves straight, and that's of limited use. So we've been doing a lot of research in this and doing some pretty neat things that allow us to do other things. So let's get into that. What is self-collimation? Self-collimation is a phenomenon that occurs in a periodic structure, a photonic crystal, where no matter what direction a wave tries to go, it's forced to go straight and forced to follow the lattice. So this cartoon on the right explains it pretty well. If we have a diverging beam, that will collimate, and it will no longer diverge inside the lattice. And it also follows the lattice. We could hit it at an angle, and in principle, once it hits the lattice, it self-collimates and follows the lattice. So it's somewhat independent of angle of incidence and will guide energy or power along the direction of the lattice. Now, once it leaves the lattice, it's no longer self-collimated, and usually it continues doing whatever it did before it hit the lattice. So here's some simulations. These are ugly simulations. I'd like to redo these, but anyway, here we are. We have a beam that's about 10 wavelengths wide, and it's converging. As soon as it hits the lattice, we have air on the top, and we have the lattice down here. Well, it no longer converges. It self-collimates, and it follows the lattice. Well, what if we keep macroscopically the same device, but we tilt the orientation of the lattice? We illuminate it with that same beam, and when it hits the lattice, it self-collimates now at an angle. So it's following the lattice. It's relatively independent of the angle of incidence. It prevents diffraction. The beam's no longer spreading or converging, and it follows the lattice. That is self-collimation. So what's doing it? Let's look first at the lattice on the left. We have a two-dimensional lattice, and so following the procedure we just outlined, we can calculate its isofrequency contour at a certain frequency. What we're looking for are flat surfaces in the isofrequency surface. So think about this. No matter what direction a wave is trying to go, phase is trying to go all these different directions. We can think of this as a beam diverging. Imagine turning on a flashlight, that beam's diverging, it's trying to go in all these different directions. However, inside the lattice, since this isocontour is flat over a certain cone of angles, the power is forced to go straight over that entire cone of angles. This is where self-collimation occurs. Likewise, with a three-dimensional lattice, we'd have a three-dimensional isosurface, but if it has a flat face, this cone of angles, that's where phase wants to go, the power is forced to go straight. And so that's the direction power or energy goes. And that is self-collimation. So we can identify self-collimation. We calculate the isocontours. We look where it's flat. And what we see is that we go from being convex to concave. Notice this is bowing out, and over here it's bowing in. So clearly it passes through a region of being flat that we call the inflection point. And if we look at the normalized frequency, we see that self-collimation occurs at a normalized frequency of this lattice anyway, of 0.335. So A over lambda equals 0.335. If we know the free space wavelength that we want it to self-collimate, we can use this relation to calculate the lattice spacing that would make it self-collimate at that wavelength. We can tailor things. We can change the lattice. It's a different lattice on the left. Clearly, its isocontours on the right look strikingly different. So the whole act of changing the lattice, changing the spacing, changing the pattern within the lattice, playing with all that, and watching what happens with these isocontours, that is dispersion engineering. And in this case, we can use it to tune self-collimation. We can make the sides with the flat faces larger. We can make them smaller. We can move them around. And there's some reasons for doing that we'll show in a few slides. But doing this is dispersion engineering. There's no band gaps. Not necessarily anyway. So again, I don't want to call it a band gap material because this can be very useful without any band gaps. But let's think more about self-collimation, how to dispersion engineer it. So we did this, and we generated a lattice. Let's start from the beginning. So self-collimation, a wave follows the lattice without diffracting. Well, if we could take a periodic lattice and bend it, well, now we can flow waves over arbitrary paths. So look at this lattice. It bends from the left down to the lower right. So this would be a self-collimating photonic crystal, but we've bent it. So if we illuminate the left side with some kind of beam, that beam would flow around a 90-degree bend and exit the bottom face here. And so here's our first simulation. It's kind of ugly, but I'm attached to it because it's our first simulation. We have much prettier things now. And here is a look at the lattice. So the blue background is showing the tilt of the lattice. And so we go through 90 degrees tilt. We illuminate it with a horn. And these red lines are our measured data. And there's about a 20 dB swing here. So we have about a 100-to-1 ratio. But we can see the beam coming out. There's also some noise, which is rather significant noise. It's not really noise coming out the other faces. And the reason that's there is because we did not do anything to prevent reflections at these surfaces. So reflections at the first surface, not a big deal. They just disappear. But if we self-collimate a beam around this bend, when it hits this surface, whatever gets reflected, some goes back in this direction, but some also reflects in this direction, then reflects again. And we get some scattering and resonances here that we could clean up if we did something more sophisticated at the edges to prevent those reflections. But we didn't do it, and we showed that we can actually self-collimate a beam around a bend. And this wasn't obvious, at least to me at the beginning, that we could do this. I didn't know if it would leak energy around the bend or what would happen. But we built one, we 3D printed it, and we showed that this can actually happen. Now, a real critical aspect here of bending the lattice, and it's a subject for a lecture coming up called Synthesis of Spatially Variant Lattices. We designed a unit cell to self-collimate. Well, if we just bend the lattice without thinking, what we'll end up doing is compressing the unit cells at the inside of the bend and stretching them at the outside of the bend. Well, we don't want to do that. We said that the lattice spacing will actually shift what frequency the self-collimates. We want it to self-collimate all at the same frequency. We need a way to bend the lattice without changing the size and shape of the unit cells. And geometrically, that seems impossible. The radius of the turns on the outside are 30 to 40 times the radius down here. Yet we see that the lattice spacing is almost constant. That's a really enabling thing. That's what makes this work. If the unit cells were really large out here and really small here, this wouldn't work at all. So the art of doing this we call synthesis of spatially variant lattices, and we have an entire lecture devoted to that later. Suffice to say, we can bend periodic structures without deforming the unit cells and do all kinds of cool things, this being one. Well, we wanted to optimize the self-collimation effect. And so this made us ask ourselves, what is good self-collimation? We had to define what that was before we could even start studying what makes a lattice a better self-collimator. And it turns out this was missing from the literature. So we came up with, or we proposed to the community, some metrics for self-collimation to try to assess how good this is. Well, one is the fractional bandwidth. Over what bandwidth will this self-collimate? Another one is the acceptance angle. We know that a beam will, wanting to diverge, there's a certain cone of angles beyond which it won't self-collimate those outside ones. Something called a strength metric, which we'll get to. And then we can tie all these together in a single overall figure of merit. So let's look at one quadrant of the isocontours. We only need one quadrant because the others just map to this. So we're looking at these isocontours in one quadrant. The first thing we can do is say we'll say that this lattice will self-collimate as long as the slopes of these lines are within some threshold angle. And if we say 4 degrees, this dashed line bounds the region in this quadrant where those isocontour lines are within 4 degrees of being perfectly vertical. So we would say that this, it looks like the top of a dolphin, is our region of self-collimation. The next thing we'll do is we'll scan along here and we'll figure out where the bands are perfectly flat. And that's called our inflection point. And that's the obvious point of where self-collimation will be strongest. What we'll see in a little bit is that's not necessarily the case. But let's think that way right now. Our flat band is where self-collimation is the strongest. That's our inflection point. So then what we would do is we would scan left and right, and we would, again, using some kind of threshold, we see that we have an upper and lower Bloch wave vector. We calculate what frequency is associated with this point, what frequency is associated with this point, which we get from the eigenvalues, and it's the difference between those frequencies that tells us our bandwidth. And we end up calculating the fractional bandwidth. So that's our first metric. Over what bandwidth will this self-collimate? And we have an optimization algorithm that actually fits the largest rectangle under this dolphin-shaped back. And that's really where we identify these widths. It's from the optimum area under this rectangle. So anyway, now we know the bandwidth. We take a look at this point. This is the worst case point. And we define an angle. And that's our acceptance angle. Remember, this is one quadrant of the isocontours. This maps down here, so we have another line going out this way, which is why we're labeling this theta A over 2. So this is half of the acceptance angle, and it will self-collimate over that entire angular span. So over this entire bandwidth and over this entire angular span, it will self-collimate. So that is our second performance metric, our acceptance angle, and we normalize it to 90 degrees. Next is a strength metric. And what we found, interestingly, that the quality of self-collimation, if you will, depends on where this inflection point is. I'll bring up again, as we approach a band edge or the stop band of any kind of filter, we know that the dispersion gets crazy. There's very often not very good properties as we get to the edge of a band. Well, this makes sense then. We want our inflection point away from a band edge. If our inflection point was way over here, we would expect a poor self-collimator because the dispersion of the band edge is messing that up. Likewise, if the inflection point was way over here, we've never actually seen one this close to this band edge. We've only seen it close to the gamma point. But if our hypothesis is correct, we would also have a bad self-collimator. So we come up with a strength metric that's a maximum of 1 when it's in the middle of this horizontal axis, and then goes to 0 as it approaches either of the band edges. So this is how we express our strength metric. And we have some illustrations of this in following slides. So our three performance metrics, we can combine all into one figure of merit for self-collimation, and it's the geometric mean of these three parameters above. Okay. Here, we're plotting this strength metric as a function of fill fraction of lattice. So we have a homogeneous lattice here and a homogeneous lattice here. We'd expect really not to see any self-collimation. So we plot that strength metric. So remember, the strength metric is higher when our inflection point is away from the band edges. So as we change fill fraction, we see the inflection point moves away from the band edge, hits a maximum, and then goes back down. Well, if we plot how this lattice looks self-collimating at different points, what we see is that, yeah, it really does look better at this maximum point. And how we generated these, we had a little dipole source, which should radiate in all directions, but due to self-collimation, it radiates in all four directions. And if you want pretty self-collimating pictures, that's the worst way to simulate a lattice. But we like it because if there's anything wrong with the lattice, this will spill it out. If you want better pictures of self-collimation, you would have a much wider beam. So, but this does confirm we want that inflection point away from band edges. So I mentioned before, the inflection point isn't necessarily the frequency where the best self-collimation occurs. And why is that? Well, just imagine we're down here. Imagine we have a low strength metric. In one regard, we want to operate at the inflection point because that's where the band is flat. However, the band edge is messing things up, and it turns out that would actually self-collimate better at a slightly different frequency that's a little bit farther away from the band edge. Because we have competing things. We want to operate at the inflection point, but we also want to operate away from the band edge. And that can sometimes shift the optimum frequency of self-collimation away from that inflection point. Last slide. We found really the best self-collimators are not the unit cells with the highest symmetry. However, there is interest in optimizing lattices with square symmetry that have the higher degrees of symmetry. So what we did is using our performance metrics, we optimized unit cells and looked at what different lattice parameters, how that affects the quality of self-collimation. So it turns out for the E mode, this unit cell on the left was the best self-collimator that we could see for a square lattice. And as I mentioned, we actually would want to deviate from being square to get a better self-collimator. But for the highest symmetry unit cells, this seems to be the best for the E mode, and likewise for the H mode. So now let's look at what happens when we play with different parameters and we look at the different performance metrics. These top two, for the E mode and the H mode, show what happens to fractional bandwidth as we change the two different dielectric constants. Well, what we see is that we get the highest bandwidth with low dielectric constants. That's pretty interesting. And that's the same conclusion for both lattices. We also see that if we need higher dielectric constants, we really want to stay with them being as equal as possible to get the highest bandwidth. We can also see that it prefers one side over the other. In this case, we want ER1 to be higher for the E mode, and the H mode, we want ER2 to be higher. That's hard to see, but it's a little bit asymmetric about this line where they're equal. And of course, when they're equal, that's a homogeneous lattice. We don't get any self-collimation from that. Now let's look at what happens with field of view. This is how much the beam can diverge that would still self-collimate. Well, here we actually get the widest accepted angle for the highest dielectric constants. And in both cases, we actually prefer the epsilon 2 to be the highest. But field of view now wants to see high dielectric constants. Bandwidth wanted to see low dielectric constants. Strength metric, let's see what happens there. Again, we have this diagonal where there is no self-collimation because that would be a homogeneous unit cell. But what we can see for the E mode is that clearly it prefers epsilon 1 to be the lowest. For the H mode, something else happens. We get a decent strength metric for low epsilon 1, but it actually wants to see a low epsilon 2. And we get a region of really strong self-collimation up here with a high epsilon 2. So this high epsilon 2, low epsilon 1 pushes us pretty far from the band edge. And likewise down here, we'd want to operate with a very low epsilon 2 and a high epsilon 1. Well, if we tie these three metrics together, and also these three on the right, and we have our figure of merit, here's what it looks like overall. And we have two conclusions. So for the E mode, we like to operate somewhere around here. And we like a low epsilon 1, or I'm sorry, a low epsilon 2, a high epsilon 1. And it turns out if we look at the maximum value here, we want epsilon 1 to be 2.5. We want epsilon 2 to be 1.0. So we want to be right around here where I have my laser pointer. Then for the H mode, something else happens. We really want to operate around here. We actually want epsilon 1 to be 1.0, so right along this boundary, and epsilon 2 to be right around 4. So right here where I have the laser pointer is the best point. But we do also see we have another peak starting to happen down here. So if we want something to operate with both polarizations, this might be a good lattice to choose. So this really would self-collimate potentially for both modes. So that is the self-collimation, and we've explained more about it than I think anybody else knows right now. So that's it for this lecture.